Greetings, calculus fans. A video today on vector calculus and three-dimensional coordinates. So in this video, we'll base our comments on the motivation that any point in x, y, z space, otherwise known as R3, can be represented by an ordered triple. So typically when we think about a point in 3 space like A, B, C, we mean that we're going a distance A on the x-axis, a distance B on the y-axis, and then a distance C on the z-axis. So you can see here sort of that the projection of this point onto the xy plane would be the point AB in the xy plane, which of course is just right here, and then the C raises this up off that xy plane by a certain distance. A couple other things here. We typically think of R3 as the set of all possible x, y, z coordinates, and we typically think of x greater than or equal to 0, y greater than or equal to 0, z greater than or equal to 0 as being the first octant, right? So the first octant is sort of analogous to the first quadrant in the xy plane. Okay, we'll talk about two things here. We'll talk about distances and vectors. So start off with distances. The distance formula from a point P to another point Q is given by the sum of squares square rooted. So this is a pretty straightforward formula that's exactly an extension of the distance formula in R2. I won't go through the derivation, but it's derived by applying the 2D distance formula twice. Okay, so an example that uses this distance formula, let's have a look at the distance from some point -2, 3, -7 to the point -1, -2, -3. So again, pretty straightforward here. Just apply the distance formula. So here we see the squares of those differences summed and then square rooted, and then all that's left is just to crank out this number. So in this case, we see that that distance is the square root of 126. Okay, a second thing that the distance formula can be used for in three-dimensional space is to talk about the set of all points that are a fixed distance r from some given point, x naught, y naught, z naught. So we'll take x naught, y naught, z naught to be, again, this given point, and think about an equation that encapsulates all points that are a distance r from this given point. So we can see here that all possible points of specified distance r from this given point, x naught, y naught, z naught, satisfy the distance equation, and it's common to square both sides and express this as a sum of squares equals another square. So just as a similar calculation in the xy plane, this gives us the equation of a sphere. This sphere has radius r and center x naught, y naught, z naught. And again, analogous to an equation for a plane, typically we'd be given some sort of equation, quadratics in x, y, and z, and be asked to find the center and radius of a sphere. And in order to do that, it turns out that you have to do a whole bunch of completing the square. So here we see the results of completing the square 3 times on the x, y, and z terms respectively. And then I'll go ahead and just rewrite the given equation where we're replacing those complete the square factors by their equivalent statements here. So here, factoring and then simplifying all the constant terms, we arrive at the equation x plus 2 quantity squared plus y minus 1 quantity squared plus z plus 2 quantity squared is 4. So we see that the center of this sphere is the point -2, 1, -2, and that the radius of this sphere is 2. Okay, second part of this video, we're going to talk about vectors. So some of you with a little bit of background in physics are familiar with what we mean by a vector. Vectors are used to describe velocity, force, displacement, etc. So vector value quantities always have a magnitude and a direction. Of course, the magnitude is also known as the length of a vector, and then parallel vectors are said to point in the same direction. So that's what we mean when we say parallel. Okay, we can do some arithmetic on vectors. So here's a notation for this class. For vectors, we say that U is a vector value quantity if it has values U1, U2, and U3. V is a vector value quantity if it has values V1, V2, and V3. And here in this example, C is a constant. So to add vectors, we add components. To multiply a vector by a scalar, we just multiply each component by a scalar. And the magnitude or length of a vector is the sum of the square of those components square rooted. So in this example, we're going to find two quantities. We're going to find the vector 2 times u plus 3 times v, and then we're going to find the magnitude of the vector u minus v. So first, 2u plus 3v. So we can see here the first step, scalar multiplication, right? Multiplying each scalar by each vector by the scalar, and then the second step, vector addition, adding the components, and we end up with a new vector, and that new vector is 31, -4, and -5. So in the second part of this example, we'll find the magnitude of u minus v. In order to find the magnitude of u minus v, we first need to find u minus v. So here's u minus v, and of course by u minus v, we really mean u plus -v. So u plus -v is 3, 3 minus 5. And then we'll just go ahead and find the magnitude of that resulting vector. So just the square root of the sum of the squares of those components. 9 plus 9 plus 25 is 43, and the square root of 43 is the magnitude of u minus v. Okay, super. Just a comment about the zero vector. The zero vector is a special vector whose components are all zero. A couple of special things about the zero vector. Any vector plus the zero vector gives you back the vector you started with. And the magnitude of the zero vector is 0. In fact, it's the only vector whose magnitude is 0. Okay, so again, the zero vector is known as the additive identity. And if you get a magnitude of 0 out of any vector, the only way that's possible is if that vector is the zero vector. Okay, talk a little about unit vectors. We call a vector v a unit vector if its magnitude is equal to 1. Now, the vector u hat, that is u divided by its magnitude, is always a unit vector, and it's always parallel to u. So we usually call this process of finding a unit vector parallel to u normalizing u. Also, if u hat is any unit vector and you cook up a new vector and call it k times u hat, that new vector is always parallel to u hat, and it has magnitude given by the absolute value of k. Okay, so a couple examples here with unit vectors. First, we'll go ahead and find a unit vector in the direction or parallel to -2 to -1, and then we'll find a vector of a specified length in a specified direction. Okay, so first, in order to find a unit vector in the direction of a given vector, this is again the process of normalizing a vector. So we see that the magnitude of u is given by 3. So this new vector, 1/3 times -2 to -1, is guaranteed to be a unit vector, and since it's a scalar multiple of the given vector u, it's in the direction of u. For the second half of this example, we see that the magnitude of the given vector 6, 2 minus 3 is 7. So therefore, 1/7 times 6, 2 minus 3 is a unit vector parallel to 6, 2 minus 3. Now, of course, if we want to get a vector of length 4, all we have to do is multiply that unit vector by 4. So the desired vector is going to be 4/7 times 6, 2 minus 3. Okay, so again, building unit vectors in a specified direction, just divide by the magnitude of the vector in the direction you want, and then multiply by the length you want if you need to. Okay, a quick comment about a couple special unit vectors. The standard basis are special unit vectors. They're I, J, K, and they're special because they're unit vectors, obviously, and they can also be used to describe any vector. Okay, so again, these all have unit length. That's pretty clear. And we can express any vector u given by components u1, u2, u3 as u1 times I hat plus u2 times j hat plus u3 times k hat. This is going to be a useful expression that we'll use later on to describe, to do vector arithmetic. Okay, finally, a quick example illustrating the usefulness of vectors. One of the reasons they're useful is to talk about force balances. So you can imagine if a weight is hanging here from this, these two ropes, we can describe the tension in the two ropes, T1 and T2, in terms of this weight. So again, this is a fairly straightforward force balance equation that we can use just a little bit of trigonometry to solve for T1 and T2. So here I've added a couple triangles with the angles 32 degrees and 50 degrees that represent the components of these vectors T1 and T2. So in order to get T1 and T2, we'll go ahead and first break T1 and T2 into components based on their magnitudes in the I and J directions, and then we'll identify a force balance that the sum of T1 and T2 have to balance this 100-pound force. So we can see that T1 can be described in terms of its components in the I and J directions. So negative magnitude T1 cosine 50 I hat because it points to the left, plus magnitude T1 sine 50 j hat because that points to the up. And then of course T2 points to the right and to the up, so magnitude T2 cosine 32 degrees I hat plus magnitude T2 sine 32 degrees j hat. Now force balance tells us, of course, that the tensions T1 plus T2 balance the force of 100 pounds pointing in the down direction, so they have to point up by 100 pounds. So that's 100 j hat. So pretty quickly we can just equate components here and find two equations in two unknowns that tell us how these vectors T1 and T2 match up to the equation. So again, just sum those vectors T1 and T2, equate the I components to 0, equate the J components to 100, and now we have two equations in two unknowns for the magnitude of T1 and the magnitude of T2. So these are pretty quick to solve. Use your favorite method for solving two equations in two unknowns, and we can find the magnitudes T1 and T2 quickly. Okay, so again, just go ahead and solve those two equations in two unknowns for the magnitudes T1 and T2, and then we'll go ahead and just plug them back into our given equations for T1 and T2 to find that T1 is negative 55.05 I hat plus 65.60 j hat, and T2 is 55.05 I hat plus 34.4 j hat. And you can see quickly that those balance to 0 force in the I direction and 100 pounds in the J direction as desired. Okay, thanks for your attention. Have a great day, and we'll see you next time. Bye-bye.